Okay, this is about my 20th attempt to try this, so hopefully this works and wasn't giving up, and you can do something else tomorrow. Question one is C. Most people got it right. With condensed structural formulas, make sure you write out the formula fully, CH2, CH3. Some of you thought it was B. It wasn't B because it's C2H5. You've got to write that out in full. Okay, just watch out with skeletal pictures. Remember, skeletal pictures, you don't draw the hydrogens attached to carbons, but there would be an H there, which is why there's an H at the end there. Question, question two, most people got right. Um, these are all alkenes. If you're not sure, please draw the molecules out fully, work out the general formula, something like that. But don't guess. You have to draw them out. If you can't see it, you can't work it out clearly. Question three was the first difficult question, I thought. Um, A and B. A was a really common answer here, uh, but B and D are also were also answers. They would also, like A. So I'm not wording this very well because I've tried it many times. Okay, so A and B and D all react with the acid. You've got a base there, you've got a base there, you've got a base there. Now, in bases, HCl and the weak acids, strong acid and the weak acid, both release 1 mole of H plus per mole of um, acid. Now, some of you seem to think, understandably, quite a common thing to think, that weak acids and strong acids, because one dissociates and the other doesn't, that the H plus isn't available on this acid. Well, that's true in water. In water, it only partially dissociates, but in the presence of a base, it will fully dissociate, just like HCl. All right, which means that A and B and D are all wrong, and C is the answer. Weak acids only partially dissociate in water, which is um, why there are fewer ions available in solution compared to if you put HCl into water, where there's lots of hydrogen ions and chloride ions available to conduct electricity. So C was the right answer there. Question B was quite surprising that you got wrong. If you're going to get questions like this, or risk getting questions like this wrong, please draw the molecule out, work out the reaction, and then, of course, with addition reactions, one chlorine goes to one carbon, one chlorine goes to the other. You even know the mechanism of that, and so you shouldn't be getting that question wrong, frankly. In NMR, we didn't spend long on it. Pretty sure it's not part of the new spec. You should check really, but I'm pretty sure it isn't. Anyway, radio waves are required in the process of running an NMR. So the sample goes into the machine. The machine's turned on, it's a big old magnet, and the nuclei line up with the magnet. The radio waves flip the spin of the um, nuclei from the low energy level to a high energy level, and then when they drop back, then again you read the spectrum from that. You were told the radio wave is required, so I saw the question, thought I'll slide it in there just in case it comes up. Some of you are getting mixed up between splitting pattern, chemical shifts, and number of hydrogen, the different things you can get from the NMR spectrum. The splitting pattern tells you how many hydrogens on the adjacent carbon, on the adjacent atom. Right, so normally that's a carbon. It doesn't have to be, but for example, this CH3 in the spectrum would be a triplet because it's got 2 hydrogens on the adjacent carbon. Yeah, we know that we can do that, but it's the language perhaps you're struggling with there. Question 7, most people got right. Some people got wrong because they didn't realise that, didn't draw the molecule right. And if you did draw the molecule and get it right, we really need to sort of realise that these two CH3s are equivalent, and so there's one signal, and there are no hydrogens on the adjacent carbon, so it's a singlet, so it has to be A there. Question 8. Now, I was a little bit generous marking with some of you, I think. Really, this name is in 3 parts. Right, you've got the F bit, which is telling you there's 2 carbons, and you have to explain that in the answer. So 2 carbons, so it's F. Fene, because it's got a C-C double bond. You couldn't just say double bond because there's a C-O double bond, which isn't the same as an alkene. And the own bit was the C-O double bond. Any 2 of those 3 points would have got you the 2 marks there. B was where we started to really struggle. Okay, lots of us got this wrong or didn't get full marks. Both ethenone and carbon dioxide are simple covalent, both have intermolecular forces. Many of you seem to think that ethenone is a much bigger molecule. The formula mass of ethenone is 12, add 12, 24, 25, 26, add 16, 42, right? The formula mass of carbon dioxide is 44, so they have roughly the same formula mass, therefore the same and the same number of protons and electrons as well. Okay, so they have a roughly the same number of electrons, roughly the same size, and so for the first one, you have to say that the London forces that they um, have or can form are roughly equivalent to each other. So that's not the reason about one being more volatile than the other. What you had to spot and go into is that carbon dioxide is a non-polar molecule because it's got polar bonds which cancel out, whereas ethenone has got a polar bond and that doesn't cancel out. It's a non-symmetrical molecule overall. And so this ethenone makes dipole-dipole, whereas carbon dioxide makes London forces only. So that was a relatively poorly answered that question, yet not beyond the realms of all of you, most of you getting it in an exam. So we can fix that up. Ethenone can be made by thermal decomposition of propanone, right? So you basically heat it up and you form this thing and this thing. You have to work out the enthalpy change of this reaction. By the way, going back to this question here, the examiner's report on that one said the question was poorly answered by the majority of candidates. They did not compare and contrast the intermolecular forces fully. Significant proportion discussed bonds within the molecule rather than the intermolecular forces. And a lot of people talked about hydrogen bonding, as did you guys, but you weren't in the real exam. The average mark was a half a mark out of 2. And most people got their mark, they got a mark by referring to the dipole-dipole. Very few people talked about the roughly equivalent London forces. So you weren't alone with this. This question, however, was answered well. So enthalpy change of the reaction is equal to the enthalpy change of formation of the products. Take away the enthalpy change of formation of the reactants. And some of you worked this out using a Hess cycle, which I like. This is a shorthand way of doing it. And the enthalpy change of formation of the products was, if you look it up in the data book, 87.2. Oh, that's the ethenone, sorry. So I didn't have a data briefing. I just had to look that stuff up. So enthalpy change of formation of products. Products are ethenone and methane. The ethenone was given in the questions minus 87.2. And the other product was methane, minus 74. Take away the enthalpy change of formation of the reactant, which was minus 248. And that came, and most of you got this, to 86.8 kilojoules per mole. And you should really be writing a plus sign there to show that it's endothermic. We don't have to. It's thermal decomposition, which means it's endothermic. So you have to draw an endothermic energy profile diagram, and then he did not. The reactants are on the left, the products are on the right. The enthalpy change is shown with an upward arrow there. That got 1 mark. Don't want to see any double-headed arrows, folks, please. I really don't want to see double-headed arrows. You go from reactants to products. The activation energy is the energy from the reactants all the way up to the peak there where the transition state is. Now, at GCSE, we teach you that's the energy required to break all the bonds, but really it's the energy required to get to the transition state from the reactant. So it starts way down here. Again, single-headed arrows, please, showing the direction of travel there. Question D was done really badly. I want to spend some time on this one, right? So you need to get this, spend a little bit of time clarifying this, I think. You got a whole bunch of peaks here and a whole bunch of ways of getting marks. Most of you that got a mark for identifying the peak on the right hand side as being the most important and being the molecular ion. And the molecular ion has an MR, or formula mass, to say, of 60. Okay, and many of you worked out that was you worked out no acid, so CH3 COOH. I like the fact that some of you uh, identified the fact that the things that go through the mass spec machine and are detected are the ions. These things are the things that are detected by the machine. So if you made it clear that the M was 60, or you made it clear that the molecule G was ethanoic acid, or the peak 60 there was the ion that ethanoic acid formed when it goes through the machine and has electrons um, ripped from it through electron bombardment, then you'd have got a mark. And many of you got that first mark, right? These things in a mass spectrometry are incredibly unstable and fall apart, and you see fragment peaks from them. There's a peak 45 in there, and you could have written it like this: M minus 15. It's a loss of 15. Right, so you should have written it like that, or recognize the loss of 15 is due to the loss of CH3. Okay, so CH3 dot has fallen off, just like it's written in your data book, the CH3 radical, the CH3 neutral species. And you might have written that as this, and would have got the mark, COOH plus. You've got to have the plus sign there. I've mentioned this plenty of times in class, and it's that thing that's the peak at 45. The peak at 43 is M minus 17, so it's the peak on the right, take away 17. To get from there to there, loss of 17, right? And that's loss of OH minus OH. And so you can draw that out as well. So it's CH3, CO. And you see that in there. These are all present. They're not all made from one another, but they're all present. But there's also, you can write it like this. You can either write M minus 45, or you could have written simply that is the CH3 plus. That would be fine, and that was 15. Okay, so you have to be really clear. These things, the peaks that you see, are positive ions. And if you weren't clear on that, I didn't give you the mark. The things that are lost, the minus 15, the minus 17, or in this case, the minus whatever it is, 45. The bit that's lost is the fragment. That's the neutral species. It didn't ask you that. It asked you to what things were, or what the peaks were. Okay, 10 centimeters cubed of ethane burnt in oxygen completely. This was done. This is a very straightforward question if you know what you're doing. And many of you didn't. There's a much easier way of doing it than you did it. Let's go through this carefully. Let's go back to setting things out as a grid A and making a note, importantly, the reactants and one of the products are gases, because we can then apply Avogadro's law. Avogadro's law says that 1 mole of any gas has the same volume at the same conditions of temperature and pressure, right? Some of you tried to work out the moles and you got the right answer by doing that. That's fine, but it's much easier simply to remember that Avogadro's law says that 1 mole of any gas, regardless of the gas, will take up the same volume at the same temperature and pressure. So the ratio, the molar ratios here are 1 to 2 to 2 to 1. This water here is not a gas. It's not going to take up any space. We're going to ignore it from now on. You're told initially that you've got 100 centimeters, 10 centimeters cubed of ethanol and 100 centimeters cubed of oxygen. And so I should say volume initial in centimeters cubed. And so what's happening? What's the change in volume? The volume change. Now we can see that the ethanol is the limiting reactant here, hopefully, and that the oxygen's in excess. And we can see that because it's a 1 to 2 ratio. And so this would react with 20 centimeters cubed of oxygen, and all of this would be used up. So minus 10 centimeters cubed of that, and 20 centimeters cubed of this would be used up because it's a 1 to 2 ratio. So the final volume is 90 of this and 80 of this. Zero, I'll start again. 0 of this and 80 of this. And the other thing we need to take into account that the carbon dioxide, we started with none, and we produce the same number of moles and therefore the same volume of carbon dioxide as we lose of oxygen because it's a 1 to 2 ratio or 2 to 2 ratio. So this goes up by 20. You couldn't just write the answer 100 to get the mark, but if you added together the volumes of the gases that are left, you will get 100 centimeters cubed. I only gave you the mark there if you showed some sort of understanding and some sort of working out. Lots of people struggled with that. If you want me to go through that again in class, I'll happily do so. Ideal gases is the next one. So I definitely think this is something you should go back and have a look at, many of you. Ideal gases, there we are. We have gases behave following all those laws we learned early in year 12, like Avogadro's law and Charles' law and Boyle's law, all those kind of things. And it assumes a whole bunch of things. I'm not going to go through them all, but it's things like we assume they take up no space, they have no intermolecular forces between them, all collisions are elastic. And those things are more likely to be true the larger the volume, the higher the temperature, the lower the pressure. High temperature because they're moving around quickly, and so overcoming intermolecular forces. High high temperature that was. Low pressure, so the gas particles are far away from each other and therefore unlikely to come into contact with each other, unlikely to get close to each other, unlikely therefore to have any intermolecular forces with one another. And that's actually the answer here that you get the mark for. So you get the mark for saying that what was it exactly? So at uh, a high, less ideal at high pressure, like high pressure, um, there the intermolecular forces are no longer negligible. You could also say for the mark that the volume occupied by the molecules is no longer negligible. That's another thing you could have said. But go back, I think, and study properly what you need to know about ideal gases because that was relatively poor. Propanone can be synthesized from oxidation of propan-2-ol. And that's that final step there. So that's the step it's talking about, right? And it can be done, propan-2-ol, this stuff, can be made either from H by addition of water. And so we've got to think what that must be. So that's water, steam, water gas in the presence of catalyst, so sulfuric acid catalyst or something. And you've learned that mechanism recently. You need to know that. So most of you got that molecule, propene. Okay, so you could have just written the word propene and some of you wrote the formula of propene. Okay, so propene like that. A double bond between two carbons there, you'd add water to it, you get propan-2-ol. Substitution is swapping, right? Swapping of one thing for another. And you've studied and learned the SN1 and SN2 mechanisms and practiced them again and again and again. That involves putting an OH in the place of where there was once a halide. So if you take CH3, CH, I'm just going to put a chloro there, could have been a bromo or an iodo, or you could have simply written chloropropane, you'd have got the mark. Draw the structure of H. I'm sorry to draw the structure there, so read the question carefully. It's a pretty small box to squeeze this into. That's because of my printing. And name of G, that had to be 2-chloropropane. If you do that in an exam like I've just done, not read the question properly, as long as you're really clear what you've done, and that's fine. The next question is answered pretty well, actually. So I'm not going to spend too long on this. Ibuprofen, number of signals. Ibuprofen is this substance down here. You have to work out the number of signals caused by the feature in the ring there. So there are 1, 2, 3 distinct hydrogen types, so 3 signals for ibuprofen. And for the impurity, 1, 2, 3 distinct types of hydrogens there, so 3 signals. The relative areas under the peak, we'll do ibuprofen to start with, 2, 2 to 1, because there's 2 hydrogens in that environment, 2 in that one and 1 in that one. And likewise here, 3 to 1 to 1. That was done really quite well, so very little time needs to be spent on that. This one we might keep it like that. Let's see. So deduce giving 2 reasons which belongs to Y. Actually, this was done pretty well by most of you. So the impurity Y, there's 2 possible spectra. You've got the spectrum over here, this one, and you've got a spectrum over here. Now, we did a little bit of this in class. But this is good practice for it. You have to talk about the presence or absence of peaks to get marks here. There are a number of ways of getting the marks. The first was to spot um, that, let's get it right. Well, that is it spectrum B impurity, and most of you got that because it's got that distinct OH there, which is an absorbance at, you should give the values, you didn't give the values, ideally the ranges or a number within the range we've done, is due to the OH bond of the hydroxyl. There we go. So that's that one. So that would have got a mark. You have to say B and get that there. And the other peak doesn't have it. It's quite broad up here, but it's not that nice broad peak in the range as given in the data book. Second way of getting the mark was to talk about the absence of the C double bond O. So if you look at the peak, the spectrum A, it's got a whacking great peak we've talked about before. So C double bond O, or absorption due to absorption due to C double bond O absent in spectrum B at 1700 to 1750. So there's no peak about here, so no great big peak about there somewhere that's telling you there's no C double bond O, so that works. Whereas this one has got a C double bond O, so it can't be that spectrum there. So they're the 2 reasons. Right, a load of multiple choice ones. The correct classification, well, the one on the left is an amine, and there's only one group coming off the amine. Remember, the naming or the classification of amines is simply due to the number of groups coming off them. It's a primary amine, it's either A or D, and the alcohol, different approach altogether. That's to do with the number of carbons coming off the carbon, and the alcohol is tertiary, so it's D. I'm just checking. Does I get it wrong? That'd be embarrassing. Lots of people got that wrong in the real exam when that was done. Apparently, we're just structural isomers. We'll just draw them out. Just draw them out. So structural isomers will have the same atoms, but different arrangement of those atoms. So in other words, you'll have different chain lengths, or you'll have different functional groups on there, or maybe side chains, all that kind of stuff. So C is the answer here. Some of them haven't got the same number of atoms either side. I've just gone through. That's true for all of them. You've got the different number of atoms on either side for all of them, apart from C. So that should be rather straightforward, and most of you got that right. Question 12 was also C. Now this is something we need to work on. So enantiomers can be detected with a polarimeter because plain polarized light is rotated by single enantiomers. One enantiomer will rotate it one way, one will rotate it another way. We can detect that using a polarimeter. Question 13. Which compound has this NMR spectrum? High resolution just means that we can actually see the splitting patterns on it. So draw the molecules out, please, to get a question like this. You'll find that the only one that makes sense is propane. I don't really want to go through it in detail because most of you got this right. The reason I want to go through it is to highlight something to you. That the hydrogens at the end here, these three and these three are equivalent. So we'd see two sets, and they would be a triplet. Those 6 hydrogens would be a triplet. Because they've got 2 hydrogens on the adjacent carbon. So that's the triplet there. That would be 6 hydrogens, and it's a triplet. The 6 hydrogens bit's not given in this question, obviously, it's just a splitting pattern. Whereas these 2 hydrogens, which are here, this integration will be about a third as tall. Be a multiple because we've got 1, 2, 3, 4, 5, 6. So probably 7 peaks buried under there if you could look closely. Which organic? This is the same sort of approach. Draw the molecules out, and you'll find only one of them makes sense and fits with the data. The only one that makes sense is the propanoic acid. The really obvious diagnostic peak right from the start is the carboxylic acid, so it had to be either propanoic acid or ethanoic acid because it's got that RCOOH, which comes up around 12. So how do you distinguish between methyl and ethanoic acid and propanoic acid? Well, propanoic acid's got CH3, CH2, COOH. So we've got a triplet due to 3 hydrogens there, being adjacent to 2 hydrogens on the adjacent carbon. And this CH2 would be a quartet due to these 3 hydrogens, so 2 peaks. Whereas ethanoic acid only have the CH3, which would be a singlet. Question 15 was also done reasonably well, I think, from memory, and it was C. Let's think about why for a second. Right, this is relatively straightforward, even without the data book, actually. When this question was first given out, it didn't have a data book. But I'm too lazy to work out if these have all got molecular formula of 60, which is what the peak should be, I think. But C certainly does have a formula mass of 60, so it would produce a molecular ion of 60. But the minus 15 to there and the minus 17 to there are what gives away what the answer is. The minus 15 is due to a minus CH3, and the only 2 molecules that have well, 3 molecules that have CH3s are C and B and D. You've also got a minus 17, which is a loss of OH. This has got an OH, and these have got OHs. The one that has both is C, so that has to be the answer. Given equimolar concentrations, which substance produces the sort of strongest signal in NMR spectrum? The answer here was D, because it would be a singlet with 12 hydrogens. So all of these hydrogens are equivalent to each other. You might remember, even though you don't need to know it, we talked a bit about TMS being the standard NMR. This will give a lovely, strong singlet peak at around 0, which allows us to calibrate the machine. The only other one that would be a nice singlet really is the benzene there. There's only 6 hydrogens, okay? This will give a double at these 9 hydrogens, and this will be a mescal spectrum. Question 17, how many signals are observed in this one here? Quite only 29% of people apparently got the correct answer with this in real life. You're in good company if you get it wrong, put it that way. There are no hydrogens here or here because look, those carbons have already got 4 bonds. So there's hydrogens 2 here, 2 here, 2 here, 2 here. So there are 8 hydrogens in total. But this CH2, this CH2, this CH2, and this CH2 are all equivalent until there's 1 peak. Apparently, people found that quite hard. You should complain about it all the time, but it was fine. Which substance has the following NMR spectrum? Again, please draw the molecules out if you can't see it straight away. Most of you won't see it straight away. Why would you? This is a molecule that we've studied the NMR of, and it's this one. It's the one from CH2. Oops. There we go. Quite wrong. So this is the only one which matches out. We've got a CH3 singlet at 2. We've got a CH2 quartet, which is here, 4.12, and we've got a CH3 triplet there at 1.2. Right, that's the only one that matches up, and actually you did pretty well on that one. So 3 different peaks, the chemical shift, the splitting pattern, the areas under the peak all match up. How many chiral centers are there? This question was quite tricky. People found this quite hard. Right, I'm going to go through all the carbons in turn. It's quite a fat pen. This is not a chiral center because there's not 4 different groups coming off it. This is a chiral center because you've got 4 different groups coming off it. So is this one, so is this one, and so is this one. The answer is 4. They all look really similar, but they're not the same. Again, same old, same old. Draw the molecule. Give yourself a chance here. This is propane. We've already drawn this earlier on. This and these hydrogens are equivalent. That's that one there, and they would be a triplet. Hard to see, and this would be a multiplet um, due to the 7 hydrogens either side. It's the same as the previous question. Cis-trans isomerism. Again, I'd encourage you strongly to draw these out. I mean, the answer is D. Hopefully, you can see straight away that it's D because it's a cyclic. And if I drew that flat, I'm not great at drawing these flat, but I'll have a go. There we go. There is it flat, looking sort of side on. The chlorines can be up and down like that, which would be trans. That's this terrible picture. That's another one. Or they can both be up or both be down, and that's cis and trans. So that's the answer. This one can't be because if you drew, this is really hard to see maybe. But if you had a double bond there, those CLs would just come straight out towards you. I think I can understand why you might have got that one wrong. That's quite hard. That can't exhibit cis-trans because if you flip around that end or the other end, you get the same molecule. And this one can't as well, same sort of idea. So although one end has got 2 different groups coming off it, the other end has got 2 chlorines. If you flip those around, you get the same molecule, right? So it can't be that one either. Plain polarized light is rotated by chiral compounds. The chiral compounds are compounds that contain a chiral center. The one here, again, draw them out if you can't see them. The one that's got a chiral center is this one here. I'm going to draw this one out only. If you're struggling to draw molecules from the condensed structural formula, just work your way along. Start from the carbon and then hang 3 hydrogens off it. I didn't bother to draw them all, but you could draw them there. The next is CH2, hang the hydrogens off it. Next thing is a C with an H and a Cl coming off it. And the last one was a CH3. This carbon here is chiral. It's got an ethyl, a methyl, a hydrogen, and a chlorine coming off. And none of the rest of them are chiral because they've all got carbons with at least 2 things being the same. Draw them out if you need to convince it. Which spectrum would show the difference between propan-2-ol and propanol? Right. All right, let's go through each of these options. In terms of the mass spec are going to be different to each other because this is kind of an oxidized, this is propan-2-ol and this is propanal. So you can't get from one to the other directly, but this has got 2 less hydrogens, right? So you have a different mass. So mass works. Infrared, well, in infrared you detect a C, sorry, I beg your pardon, you detect an OH in the infrared and a C double bond O in the infrared of this one, so that would work lovely. And the proton NMR are going to be really quite different. This has got 1, 2, 3, 4 hydrogen environments. This has got 3 hydrogen environments plus all the other differences between them, so that would be right. So 1, 2, and 3 good there. The functional group of the C double bond O, as long as it's next to hydrogens and carbons only, is a carbonyl. Done that plenty of times on our mini whiteboards. Similar to before, this is exactly the same as the question I did up here, 21 really, it's just a smaller ring. And so C must be the answer there. I'm going to check the marks because I missed anything. Question 26. What can be deduced from the infrared spectrum of a compound? And that's the bonds present. You can't detect functional groups. You can't detect any of the other things. IR just tells you bond types. Classically, C double bond O, OH are the most important ones, but there's others too, as you'll see in a minute, like C single bond O. The functional group um, between amino acids. I went through this in class with one group, and I'll go through it in class with the other groups soon. But the functional group, when you clip together two amino acids, is this thing here, which is an amide. That comes about from a condensation between two amino acids. This pen doesn't work. The amino acids that I've put a box around on the left, and the amino acids um, that I've put a box around on the right. They're not technically amino. Well, this one on the right hand side is not technically amino acid, but it's related to one. And on the left hand side, um, is confusing because normally the amino acids react through. Oh, I'll start again. So you can see why this is confusing because you've got this would have come from the carboxylic acid to cover up the right hand side. The amino bit is down here, the acid bit up here. This is the acid side chain on this particular amino acid. So that's why it's confusing the seeing that and thinking what's going on possibly. But anyway, we're going to talk about amino acids in class, and you should certainly recognize an amide. This question here threw everybody but one person. You had to, with an explanation, explain which bond you can detect in alcohols using IR spectroscopy. So the answer is the C single bond O. Nearly everybody else said OH because that's a nice peak you'd see in alcohols, and that's the feature of alcohols we're most used to. But of course, breath has water in it, and water also has OH bonds. So everybody would be given be put away for drink driving if we only detected OH bonds. The C single bond O is a bond that's found in ethanol that's not found in OH. So it has to be the C single bond and C double single bond O there is detected. And um, nearly all candidates and the real thing, the real exam, incorrectly identified OH, failing to realise it was unsuitable due to its abundant presence in breath. By the way, I've just checked the mark scheme. It also would allow CH here. So I don't know that I gave that mark. So if anyone gave OH and explained it, do let me know and I'll come back and give you the mark. Um, those of you who revised properly just wrote down the right answer for this one. Those of you who haven't revised yet need to work on this. So enantiomers, remember they're the left and right hand type of a chiral molecule. Chiral molecules are those molecules that have carbons with four different groups, like an example might be this. And you've got to practice drawing them. You're very comfortable drawing them in an exam. Something like that would do. And you've got the mirror image, which you could draw. And some of you might remember you can draw it simply by drawing the same thing again, but flipping two of the molecules. Two of the side chains around. That would be another way of drawing it. Anyway, there's the mirror image of that one. And the way that a polar image you can distinguish them is because one enantiomer rotates plane polarized light anti-clockwise, and the other enantiomer rotates plane polarized light clockwise to the same extent if they're in the same concentrations. You had to refer to plane polarized light there, and you had to talk about the clockwise anti-clockwise thing that I just mentioned to get the mark there. That's it. Hopefully, it wasn't too painful going through it.